Kansas City SQL Server User Group. Thank you everyone for joining. We are happy to welcome Erland Sommarskog to our user group today, presenting perhaps the best lunch and learn title ever. Don't bite off more than you can chew, take it in chunks. For US folks, this may be a lunch and learn, but don't feel left out if you are joining us from somewhere else. Feel free to have any meal or perhaps a midnight snack if that's your preference. For the audience, this session is recorded and will be uploaded to our YouTube channel. If you have any questions, feel free to ask them or pop them in the chat as we go along. Once the recording is ready, I will place the link inside the Meetup event and post them far and wide on various social platforms. If you miss any of those, you can check out our YouTube channel at any time to see our latest and greatest listings. And as usual with our Lunch and Learns, we jump right in. And with that, I'll let you take it away, Erland.
All right. So welcome to this session entitled, yes, don't bite off more than you can chew. Take it in chunks. So don't eat all your lunch in just one single bite. No. There might be a time way back then, you were a junior programmer and you asked a senior colleague and said, I have this table, I need to loop over it. How do I do that? And your senior colleague looked at you and smiled and said, no. In SQL, we don't write loops. We write set-based statements. We work with all data at once. And as you progress with your career in SQL, you came to learn these set-based statements. You come to learn them. They come to love them. It became a way of life for you. But then every once in a while, you might have encountered this really, really big table, and you might have thought, should I really work with all data at once? Maybe not. Maybe you should take it in chunks. So let's see. I need to get the focus on, because I'm presenting off a VM, so I need to get the focus on the VM before I press next. So my name is Erland Sommarskog. I live here in Stockholm, Sweden, where I work as an independent consultant, and I've been a PEEP for SQL Server and data platform for many years. The way to get in touch with me is by old-fashioned email, sql@sommarskog.se. And if you have any questions related to this session or anything else but SQL for that matter, please feel free to drop me a line. I also maintain a website, sommarskog.se, where you find a couple of longer articles about various topics. However, this is something I only have as a session. And slides and scripts for this session is available on my website, sommarskog.se/present, where you find all my sessions, and this one is currently on the top. So let's see here. This is the agenda for today. So I'm going to start with discussing two scenarios where chunking comes into play. Here with some kind of cryptic subtitles. Don't bite off more than you can chew, and be nice to others. Then the main body of this session will be about how to implement chunking, talking about performance and other pitfalls and things we have to think about. And the last thing I will discuss is how to use chunking for error handling, here with a cryptic subtitle, when all or nothing is not what you want. So let's say this, you have a table and you want to perform some operation on the entire table or the better part of it. It could be that you have realized that in column, which is the primary key, that wait a minute, there's 10 digits and it starts with a 2, which means that it's very, very soon will hit the ceiling. So you need to change that to a big hit. And of course, you can do that with all the table. But you may also decide, no, I'm going to create a new version of the schema and copy all data over in a single insert statement. Or it could be that you have added a new column to your table and you will now want to initiate that column with some value, maybe a constant, or taking values from other tables and so on. Or it could be that you're looking to a purge operation, for example, that getting rid of 50 or 90% of the rows. If you want to get rid of all rows, well, that's simple. You can use truncate table, but let's say you only want to get rid of some of them, but a substantial part. Now, say that this table has a size of 300 gigabytes. What can happen if you just will do all this in one single statement? Hey, it could be your lucky day and everything may go just fine. However, much more likely is that the log file will start to grow violently and eventually overflow the disk. Or it could be temp2b. Both the data and the log file on temp2b could grow out of bounds. Maybe operation is more complicated than I suggested on the previous slide, so you use temp tables and they fill up, you just completely explodes. Or that could be more complicated query plans with spool operators, or etc., that spill to disk, etc., etc. There's also a question about the buffer cache. So let's say you're going to update all these rows, and if you only with single scan, it's quite simple because they're being read into cache, and then with the next row needs to place already. Eventually, you have to read more data, so the table does not fit the table doesn't fit into memory, but if it's just one single location, you will read it into cache, it will go out again and so on. But if you have to go back to the same row multiple times, every time to read it from disk, oh, it's not going to be fun. And also, you have to think about the rowback. I mean, what if you, or rather, if you have to cancel an operation, the rowback could take a very long time. Of course, normally you're not going to row back, but it could happen that you have to do that. And the remedy for all of this is to split up the work in chunks. So rather than working with all data at once, you work with reasonable subsets of the data. And of course, the chunk size should be small enough to avoid log file and temp-db explosions. But at the same time, don't make it too small because the chunking will add overhead and the bigger chunks are more efficient. Now, the obvious question now is, okay, so what is the right size? How many rows should I have in my chunk? And you already know the answer. It depends. Of course, it depends. It depends on a lot of things. For example, what is the current size of the log file and temp-db? And how much can you permit them to grow? Let's say you already have a 10 terabyte log file. Well, then you can probably handle that 300 gigabytes table in one go. But it's also not only the number of rows, it's also the size of the rows. So an extreme example here, you have only 1 million rows in the table, but there is a log column which you need to work on, and it has an average size of 1 megabyte. You're looking at a 1 terabyte table. But apart from that, I mean, it's also a big difference if there are 500 million rows and there are just 4 tiny int columns, or there is just 200 columns in white. That makes a lot of this of the number of size in bytes. Now, all that said, I do have a kind of standard value that is 5 million rows. And it's not taken out of completely thin air, because a couple of years back, I had a situation where I had a table that was not extremely wide, but still 40 to 50 columns, and I wanted to make some changes to it, and I had actually have a tool that generated these loops and was thinking, what is actually a good chunk size? And I found that when changing the chunk size from 500,000 to 5 million rows, I still gain performance by, well, let's say 10-15%. Then I said, nah, given the server I have, this is enough. But as it says on the slides, your mileage may vary. Now, I like to remind you about the transaction log, because even if you split up the work in chunks, the transaction log may still explode if you don't back it up frequently enough. And normally, you may only have back up the log like every 15 or 30 minutes. And that could be too rarely or too seldom when you're doing these large operations. So you might have to increase the backup frequency to do it, let's say, every minute. And of course, you also need to make sure that you have space for the log backups, because you will produce a lot of transaction log, no matter you like it or not. Now, be nice to others. This is a different scenario, and maybe also smaller situation. In the previous, I assume it more or less it was something you would do in a maintenance window where you have the server to yourself, so you don't have to think about other users. Now, this might be a small operation, maybe only 5 million rows in total. However, it will execute in the live system when there are other users. So you would impact those users if you try to handle all those 5 million rows at once and take up too much CPU, memory, etc., or also cause blocking or deadlocks. Now, again, the remedy is to split up the operation in chunks, now this time with a fairly small chunk size. This means that your operation as such will be less efficient. However, the overall system health will be better. Now, in this case, there is kind of a magic number that you have to look at. And I say kind of because it depends on if you have to consider lock escalation or not. But let's say you're writing a purge procedure and you're going to delete rows from the left side of that table, while the users are mainly looking at the new data on the right side of the table. And you don't want to block these users, so you want to avoid lock escalation. And you know that you may know that when a query takes more than 5,000 locks approximately, it can escalate to a lock on table level. Now, this is not always the case. Maybe you're writing to a table that you have for your own. In that case, you don't have to think about this one. You might still have a bigger chunk size. But let's say, in many cases, this is an important thing to consider. Now, if that is something you want to have a look at, you can actually run a test operation with different chunk sizes to see what kind of locks you get. So let's take a look at that. So here I've got a database called BigDB. This is the demo database for today. And I'm going to start a transaction, and I will delete 2,500 rows from a table called BigTrans that I will come back to a little later. Then I'm running this query from system_tran_logs. I'm looking at the resource type, which is what sort of thing am I locking, the request amount, in which way I'm locking it, the resource associated identity IDs. What am I locking? And that might be an object ID. In that case, I try to translate that to a table. And how many do I have of these kinds? And this is the DMV that have all the locks, and I filter it for my own SPID. I do a group by, and then I do a rollback. So let's run this. And we can see here, first of all, I got one shared lock on the database, nothing strange about this. Then I got two key locks on two different things. That is the clustered index and the non-clustered index. And that's 2,500 of each, so they are row locks. Now, you might also see that all locks on object level on the table, but that is an intent lock. An intent lock means, well, basically, I'm here doing work, just telling, so it's just a marker. The intent locks are not a problem. And same goes for the page locks. They are not an issue. But so this is good. But let's see now what happens if I increase this to 3,000. I got a lot less lock this time. I got one share lock on the database and one fat big lock on the entire table. So 2,500 was good in this case. 3,000 was not. So just to summarize, when you do this exercise, you should see exclusive locks only on key and RID resources because they are row locks. Key are locks in indexes, RID are locks in heaps when you don't have a clustered index. If you see X locks on an object or page, well, then your chunk size is too big. Well, actually, if you see X log on page, that is not due to lock escalation, because escalation is always at table level. So if you have X log on page, that could suggest that the indexing is not perfect, and you may have to review that. But if you see intent locks, IX locks on object or page, they are okay because they are only just a marker. I'm down here. You would block users that would have to, that for some reason would like to scan the entire table, but you may have to accept that because that is a lot more difficult to deal with. Now, let's now talk about the challenging with doing chunking. So it's not that chunking is like a wild adventure going on a multi-day hike. You need lots of equipment, emergency telephone, and lots of stuff. No. But it's not really a walk in the park either. I mean, it's like taking a forest walk. You need some sturdy shoes because you may have to negotiate a stream or two. You could trip on a branch. You could slip on a stone. So you have to be a little bit careful. First of all, you need to write more code. This means that there is more code that can have bugs, and there's more code to test. Also, how is the application affected of the chunking operation? And what if the work is interrupted halfway through? How to deal with this? And most of all, performance. Because if you do it in the wrong way, the performance may be so bad that it's actually even worse than if you hadn't done chunking at all. And I will discuss these matters more or less in the reverse order than they are on this slide, starting with performance. So here is a first chunking operation for today. And the question is this a good chunking operation or not? So and initiate this variable chunk size to 5 million and also initiate the row count to the chunk size. And then keep on looping as long as the row count is equal to the chunk size, because the last update is likely to deal with less rows than the full chunk size and the full chunk. So I know that if I did that, I can skip. And what I'm doing here, this is the scenario. I have added a new column to my some big table, and I'm going to issue to some value. Maybe it's a subquery that takes data from other tables. And assuming here also that I'm going to do this, eventually all the values for this column will be not null. So I'm just saying where a new column is null. Now, is this a good chunk operation or not? And the answer is no, it's not, because, well, on the first operation, it will be quick. SQL Server will find 5 million rows. Yep, we update these. Next time, SQL Server has to go through all these 5 million rows. Oh, here are 5 million rows we can update. Next time, it has to go through 10 million rows, and before it can find rows. So let's say that the table in total has 500 million rows. So this will be akin to doing 250 full table scans on this table. So it's not a good operation at all. It's just going to scan a lot. It's going to take a lot of time. So here is something very, very important. Indexing is critical. When you define chunks, they must always be over an index column. Because if you don't do that, you will scan that big table again and again and again, and it's going to be really, really bad. And the larger that your chunk size is, the more imperative it is to base the loop on the clustered index. Because let's say you try to use a non-clustered index and the optimizer looks at this and says, wait, 5 million kilocubes. That's very expensive. I'm going to scan that table. So now for smaller chunk sizes, a non-clustered index may work, but still there may be kilocubes, which is going to slow down the whole thing, which you might avoid if you're using the clustered index. However, I need to qualify this because there might be business logic that says that, well, we need to deal with the rows in this order, or it could be that you are joining to other table, and that could affect which the choice of index you should use. And we will see an example of this briefly later on. Now, big trans. So I'm going to talk a little more about this table. So it has 31 million rows and it has a size of 2.2 gigabytes. And I found this table from a blog post from Adam Mechanic. It has a big adventure works. It's big to be a demo table. It's still small to be a real world table. And anyway, this table has 5 columns. There's a transaction ID, a product ID, a date, a quantity, and amount. And there's a primary key. On this one is a primary key, and this one is a foreign key. Now, what I want to do, I want to change the primary key to big int, and I also want to adjust the data types here that I think are a little bit funky, and also make them not null. And there is also non-clustered index on the product ID and transaction ID, including these two. So now, if I want to make all these changes to big trans, how can I do that with all the table? Well, first of all, I need to drop the primary key and the non-clustered index and recreate them at the end. And I need to run 4 alter table, alter column statements, all rebuild the table, because you can't alter more than one column at the time, unfortunately. So when I tried this, it took 984 seconds, and the transaction log grew by 70 gigabytes, and I started on 700 megabytes when I did this. So I said, let's try another way. So I created a table called new trans with a clustered index in place, but without the foreign key and the non-clustered index. Then I copied all the rows in a single insert statement, and then I created the foreign key and non-clustered index. And I did it in that order because that was faster. Now, the execution time was down to 6 to 8 seconds, but the transaction log still grew by 7 gigabytes. So let's see if we can improve this further by doing chunking. So I'd like to introduce you to a generic way to drive the chunks. So first of all, this is a procedure, and it takes the chunks as a parameter. Now, the only reason I have it this way is because I ran tons of tests when I did this session. So trying different various tweaks, I'll do it this way, that way, and so on. So it was practical to make them to procedure and make the chunks as a parameter. Now, for something like this, what would be something you would do in a maintenance window, you would make it single script, and you would probably hardcode the chunks as that would be all right. But the rest illustrates how we can drive the chunks in a way. So in a good way, in a generic way. So I got min ID and max ID. Those are my chunk boundaries. Then I got the lower boundary. Initially, the lower boundary to take the min transaction ID from the big trans table. Then I keep on looping as long as this one is not null. Now I have this subquery saying select top chunk size transaction ID from big trans where transaction ID is greater or equal the lower boundary, or where transaction ID ascending. So now when I take the max of this subquery, I get the upper boundary. That gives me exactly chunk size rows. And then I copy these rows, quite simple, insert new trans, select from big trans for transaction ID between those. And the last thing I do in the loop is to get a new lower boundary by taking the next transaction ID, which is bigger than the current upper boundary. Then I quit the loop, and at the end, I recreate the non-clustered index and the foreign keys. Now, I like to dwell on this pattern a little bit. You might be thinking here that, well, wouldn't it be easier just to say max ID equals min ID plus chunk size minus 1 or something like that? Well, in this particular case, it would work because the keys in big trans are actually contiguous, but there could be lots of gaps. So maybe you would only get 3 rows in a chunk. That would be inefficient. But not only that. This pattern does not only work with ints. It also works with dates, strings, grids, even floats, anything you can put an index on. It even works to some extent with multi-column keys, or which I will come back to that later on. Now, so how did this fare? So first of all, I'd like to remind you that the times you see here includes restoring the foreign key and the non-clustered index. So it means that the consequences of the chunking operation are somewhat dwarfed by this constant time. But I wanted to compare to the real operation that I was trying to mimic. And you can see here that for the smaller chunk sizes, there's a really penalty for this. Why is that slow? Well, we'll come back to it. Sorry, I will come back to that in a second. But it is quite a bit of overhead for doing those small chunk sizes. We can also see here that as long as the chunk size is below 1 million, there is no log growth, except for the smallest chunk size for some reason, I don't know. Now, when it comes to these times, we can see that this one is the best one. But of course, it's only 1 second, so it is maybe not even significant, but you can see it's kind of a sweet spot here. The largest chunk size where the log doesn't grow. And because since the log, because you know when the log grows, it has to be zeroed out, which of course takes some time. So we have to pay a penalty for that. Now, I'd like to remind you, this table is only 2 gigabytes in size. In a real life scenario, you wouldn't dream of doing chunking over this table. And also data is from our laptop, actually not the laptop I'm using right now, but an older one that I had. And your testing may yield different results when you try it on your own hardware. Now, excuse me, I'm just going to have some water. Now, that's one thing we need to consider here. So the optimizer does not know the values of at min ID and max ID, and therefore it will just make a blind 9% about the hit rate, just out of the blue. Which, of course, for this loop may not matter that much, but if you're joining to other tables, it could have quite big effect. So a couple of years back, this happened to me. I was working with a table and I realized, I want to add some more columns to this table. So I constructed a loop. I had a tool I generated, and I joined in those queries, etc., and joined in those tables, etc., etc. And it worked fine when I tested it because I only had 30,000 rows in my test table, in my tested base. But when my client eventually took it to their customers and they ran a test upgrade, thankfully not production, just a test upgrade, it took 12 hours at one place, and I think they gave up after 24 hours at another site. So when I heard about this, I said to myself, this doesn't seem difficult. What can I do with this? And the problem was I was not working very much with that client anymore. But before I came around to really look at it, another guy, really smart guy at that side said, try Opsharikapal. Boom, that was it. Because now, with Opsharikapal, the optimizer knew the values of min ID and max ID. You can see, we're going to work with that amount of many rows. Now this plan will be the best one. So now it had previously taken 24 hours, it now took 24 hours. Where it previously had taken 24 hours, it now took 20 minutes, which is perfectly adequate. Now, of course, if you have small chunk sizes, Opsharikapal is going to give quite a bit of overhead. Let's say that it takes 100 milliseconds to do the compilation, and if it takes, then if you go for 5 million rows, let's say it takes maybe 30 seconds. Of course, those 100 extra 100 milliseconds is not an issue. But let's say you go with a chunk size of 1,000, and that takes 100 milliseconds to process, then of course that compilation is quite expensive. Now there is one alternative though. Rather than to avoid this, you can make the chunk boundaries as parameters to make them visible to the optimizer, so you can sniff the values and then produce a cached plan. So you would have to push them into the scope. So, for example, writing a procedure where these will be parameters. But of course, as I said, this might be a bit just a script, so having a procedure is kind of awkward. But you can do this. You can simply use dynamic SQL. Well, this is not particularly dynamic, it's very static, but now min ID and max ID will be parameters, so the optimizer can sniff the input parameters and then produce a cache plan based on these values. Now you might say to yourself, but in this case, but this is a trivial plan, it can't really not matter at all here. Yep, I thought so too, but look here at these values. I got a drastic improvement with dynamic SQL. And why? I don't really know. Because the query plans is the same, but there might be something we don't see, like how it talks with the storage engine, and which also they might have improved. We're going to come back to that in a second. You can also see that with Opsharikapal for the chunk size of 1,000 also gives an improvement, if not as big, and for 5,000 it's actually more expensive than doing nothing at all. Now, then you might see it's also more expensive down here with Opsharikapal. That is not because of the compilation overhead. In this case, there is a small difference in the plan, intended to be an optimization, but apparently it backfires. Now, there is one thing I need to point out here. So this was the values when I originally wrote these sessions way back in 2019 with the build of SQL 2016 that was current at the time. I have ran these tests a couple of times for later versions and even for later versions of SQL 2016. And now the difference is not equally starting, but there is still a difference. It's still faster with using dynamic SQL. I think for SQL 2019, it was the 145 milliseconds. I reran this also in SQL 2022 on this laptop, so it's not really comparable, but still maybe smaller difference, but still a difference. But I kept these values because they were just more interesting. Now, we're going to look at the different chunking operation because we're going to make some different relations there. So I got two tables here called big orders and big details. And what I've done is or the scenario I'm playing is that I have added a column called total amount to big orders that I want to initiate with values from the big orders table and the big details table. And big orders has 5.1 million rows and it's 1 gigabyte in size, and big details has 50 million rows and 3.8 gigabytes in size. Now, when I did this, I got a surprise because dynamic scale was conspicuously slower than the plane, which plane is doing nothing at all, just doing a plain simple loop without option recall or dynamic scale. And I scratched my head and wondering what's going on here. But I found out the reason. It turned out that for big trans, I had full scan statistics, but for big orders, I had sample statistics. And the lowest I did in the histogram was 13,063, which means that for these two chunk sizes, the first chunk was entirely outside the histogram, and the optimizer thought, one row, and built the plan based on that estimate, which was not the most optimal. So when the chunk size is 25,000 rows, the first chunk is inside the histogram, optimizer makes a better choice. Now, one way to deal with this is, of course, to do it update statistics with a full scan, and the times you see here includes the update statistics with full scan on the primary key only, the index I'm using. Because if you say update statistics big orders with full scan, it's going to update all statistics with full scan, which means that particularly all non-indexed columns, there will be a full table scan. So let's say there are 50 such columns in the table, 50 full table scans. That is not going to be very smart. So you should do these update statistics only for the primary key in this particular case. And even that, if the table is really big, might not be feasible. An alternative, which I haven't tried out, but which of course should work out, is to make sure the first chunk is in the middle somewhere. So you will be inside the histogram. That should also work. But then the loop will be a little more complex. Now, I also like to discuss why we should use dynamic scale and option recall patterns and stress why we use them. So these are the values for the same operation with the big orders table, but the difference is now this version of the big orders table, the clustered index is on custom ID and the primary key is non-clustered. And look here, what happens? And just for the sake of it, assume here that these values are not 1,000, but let's say 1 million, 5 million, and so on. And these times are not seconds, but minutes. This is 3 full days. It's just complete total disaster. So, and it may not matter if it takes 96 or 127 minutes or seconds, whatever it is, but we don't want this. So that's why we're using option recall and dynamic scale to avoid the complete total disasters. Also in passing, you may note here that this one is using the clustered index. This here, the loop is over the non-clustered index, but you can see it is actually fast in most cases, because this aligns with the big details table, which still has the clustered index on the order ID. So this is what I alluded to earlier. It may sometimes be faster using a non-clustered index if that aligns better with the rest of the query. Now, let's look at multi-column keys. So this big details table has the primary key and the clustered index on order ID and product ID. And the way I've created that table, there can be up to 600 products per order. So let's say we need to do something with big details and we need to handle all the rows. Could we just ignore the product ID and run a top loop over order ID only? And of course we can, because let's say we go for a chunk size of 5 million, and well, yeah, we could get a chunk with 600 extra rows. Doesn't matter, that should work out. So now the interesting thing is you want to stick to this pattern as far as possible, because the alternatives are not really palatable. But of course, you could have a situation where, let's say we have 10,000 products per order, and take it here that it's just any table with a multi-column key, and there could be 10,000 rows for each value for the leading key. And you need to be nice to others. You need to avoid lock escalations. And you can't not exceed a chunk size of 1,000, because the more indexes there are on the table, the smaller your chunk size must be to avoid a lock escalation. So in this case, we need something else than just doing that plain top loop. Now you might say, well, we can just extend that top loop to use 2 more keys. Well, let's have a look at that. Now, I should warn you, this may go a little bit too fast for you, but if it does, you have kind of gotten my point. So this is update price simple. This is the same type of loop as we had before. I get the min ID here, from smallest order ID from big details. I keep on looping. I say, okay, give me the max order ID, select top chunk size. So the chunks may be slightly more bigger than chunk size, or substantially bigger, all depending on how many orders or how many products there can be per order ID. And then I do my update, and the operation is a really, really silly one. Just testing something, I'm just multiplying the price by 1.2. But I'm using option recompile here, and then, yeah, it's the same type as before. But let's now say this. I want to make sure that my chunk size has exactly the chunk size, that number of rows, not bigger. So here is update price, a double, which has to take care of both keys. And first of all, I need more variables. I need 2 for the lower boundaries, the smallest product ID, and the min order ID and min product ID. And the upper boundary, again, max order ID and max product ID, and also the stop order ID, stop product ID, and the game over variable. And I start with getting the first lower boundary, and I use the select top one with the order ascending, because I can't use min on both, because I want the smallest order ID and I want the smallest product ID on that particular order. I also get the last order and the last product, which I'm going to use inside my loop. I keep on looping as long as this variable, game over, is not 0. I explicitly set the max order ID and max product ID to null for reasons I will return to in a second. Now, again, I got my select top chunk size subquery here, but now as you see, it's in the CT. And I also use a row numbering here. And for big details, where the order ID is equal to the lower boundary, or the product ID is greater or equal to the lower boundary, or the order ID is just greater to the order boundary. And then I do this row number, and I pick the row where the row number is equal to chunk size. Now, for the last chunk, this condition is not likely to hit any rows at all. And what happens in this case with these variables? Well, if you have a select with variable assignment that does not hit in rows, no, the variables are not set to null. They retain their values. And this is why I set them to null explicitly up here. So if I do get null, it's game over, and I set max product and order ID to these stop order ID and stop product ID that I had saved. Now, then I go do the update, and this is a bit complicated because there's lots of cases to consider. First of all, did I move to a new order at all? Well, if I did, well, I have to take the last couple of products on the first order, the first couple of products on the last order, and all orders in between, and I combine this with these OR conditions. Or it could be that I'm staying within the same order, and then the condition is written that way. But it's game over. If it's not game over, I need to find the lower boundary for the next chunk by doing this top query, again, where the order ID is equal to max ID and product ID is greater than the max product ID. Or ID is greater to the product ID, because I might be on the very last product, the previous chunk. Now, when I tested this, I found that performance, particularly for the smaller chunk sizes, was not very good. And when I looked at it, I found that the reason was this update statement, because these all conditions make the optimizer to think, oh, I need Halloween protection, and added the spool operator that was expensive. So I had to make a new version, and this is update price triple, as I call it. And what I've done here is the same logic, but I've split up this update statement in 3, and this one performed almost just as well as the plain top loop in my test case, which was on a table where I had up to 600 products per order. So, if you thought that I was presenting this too fast, you're kind of getting my point. I don't like this solution. It's very complex, all I do with 2 keys. I just imagine doing these with 3 or 4 keys. So I'm inclined to look for alternatives. So this is a fairly simple-minded approach, what I call the big temp table. So I got a table called hash chunks, has an order ID and a product ID and a chunk number. And there's a clustered index on with the chunk number as the leading column. And I fill it up by taking all the keys and I'm doing computing the chunk number by taking row number and integer division with the chunk size. And then I set up a static cursor to get all the chunk numbers from the chunk. So then I, starting my cursor loop, get all the get the chunk into this variable chunk node, and then I do my update here, where I'm saying update big details where it exists in this current chunk. Now, here are some things to observe how this table is set up. So the chunk number is the leading column, and the order ID product ID follows. The result of this is that this subquery addresses an adjacent set of rows in big details physically. And there is a point with that, because there are optimizations for this case in SQL Server. I also made a test where I constructed the chunks table in such a way that the rows in the chunk were scattered all over the table. And it was I think 4 times slower or something like that. So this is quite important to have it this way. Now, just to repeat, so we have each chunk has a contiguous set of keys for efficient torque. That is very, very important here. But compared to the tripod top loop, yes, this was slower. In the best case, only 1.3 times slower. In the worst case, almost 6 times slower. And that might be because that joint did not have the best career plan. I haven't really investigated that. Now, I'd like to point out that in this case, the profile of the table is going to matter a whole lot for the results. So if you're going to test this with your table at home, you may get quite different results, but you might get some idea what's going on. And there's no discussion. We are sacrificing efficiency for simplicity here. Now, this was, as I said, was the big temp table, and it has as many rows as the actual table, but it's narrow because the real table could have this amount of rows, and this one only has the key values. But it still requires a full scan to fill, which can block writers, and it's still going to be quite big. It's still going to be lots of rows. So no, this is not always a viable solution, or not always a good solution. I think this is still a viable technique because it's simple. I mean, it's simple. But an alternative is a small temp table, which you fill up one chunk at a time. This is again more complex, maybe not as complex as a tripod top loop, but more of all, it's also leaner than the big temp table. So this case, the variables have slightly different names because they have a slightly different function. So it's now called color already, last product ID, and there's also a row count variable, which I initiate to the chunk size. And I again have my temp table now only with ORD and product ID. And I initiate current ORD to the smallest ORD -1 in the big details table. I keep on looping as long as the row count is equal to the chunk size. And I start with truncating the temp table. That may seem a little funny, but it's a loop variable, and I like to initiate loop variables in the beginning of my loops. And then I fill it up with the top three. So I say select top chunk size ORD product ID from big details, where ORD is equal to the current ORD and product is greater than last product ID. Because in fact, they are actually the upper boundary for my previous chunk. And also then ORD is greater than current ORD. I capture the row count, so I know that was, because if this was the last chunk, it was probably smaller than chunk size. And then I do my update, and again, we have an adjacent set of rows in the chunks table. And the last thing I do is I get what was the upper boundary of this chunk by doing this select top one query with ORD descending and product ID descending. Now, in my test compared to the tripod top loop, it was, well, again, 1.3 times slower in the best case, and the worst case, more than 3 times slower. And again, maybe not the best choice of a query plan. And compared to the big temp table, it was up to 5 times faster. Here again is a link to the same script as before. I'm not going to open it again, but there are more procedures in this script, some couple more variations, including one where the keys are scattered, and there is also some performance data in comments in that file. Now, I'm going to leave performance behind and discuss a little bit about the application impact. So if you don't do chunking at all, well, everything's just one transaction, which means that the application and the users will see nothing of the operation or just the complete result. But if you do chunking, well, the application may see some data that is processed halfway. How will the application behave in this case? How will that appear to the users? And this is even more pronounced if the operation is interrupted, which could be by accident or by purpose. Because let's say this is something you can only run in the wee hours of night, so it cannot run daytime. So it might remain half processed over the rest of the day. Now, I can't tell you. You might have to think out for yourself. It could be that you can just shrug your shoulders. It's not going to matter at all. But it could also be that you have to make substantial changes in the application. And just as a hint, let's say you have one operation which is a monolith today, just one single transaction, and you decide, I'm going to do chunking. You may find that it's going to have impact on the application. But again, it's up to you. Now, let's talk about resuming chunking. So your chunking operation is running, but for some reason it stops. It could be that the server crashes. It could be because, well, you decided, no, it must stop now because users are coming into work. It's too expensive to have it running right now. We have to continue later on. And we're going to look at 4 canonical cases and discuss what effects what might happen. So we're going to start with a purge procedure. And so we're setting a purge state and chunk size. And this is also another pattern to run the chunk. So we have this big trans table, and we're going to purge all rows that are greater than trend date. But there is in big trans, there is no column, sorry, there is no index with transaction date as the leading column. So what I do here is I do the scan, I take the row number and compute the chunk number by doing integer division with the size, but I don't materialize that this anywhere, but I'm just going to take the min and max to get my chunk boundaries, and then I do a cursor over this, and then I do the delete operation. Now, so this operation is running, and then it stops, and we won't need to restart. Now, how do we do that? Is anything we have to think about? Of course not. What has been deleted has been deleted. We can just restart and smile and be happy. Now, here we have insert top plane. This is the one before. I copy data from big trans to new trans. So let's say if this one crashes halfway through, can we just restart and smile? No, we cannot, because it's going to die immediately with the primary key violation, because it's going to try to copy the same rows once again. But thankfully, there's a very simple remedy for this. So this is insert top restart, where I start by looking at new trans and say, okay, if I have something in new trans, take that and add one. I'm assuming here that nothing comes in between and inserts data beyond my copying, because if that would happen, that would probably be problematic anyway. Then here I've got update absolute, and an absolute update means here that I'm setting the column to something which is not depending on the column value, current value. And this is again the situation. I've added a new column to my table, and I'm going to initiate it to some value. I'm using dynamic SQL here. And if this one crashes or stops halfway through, can I just restart? Yes, I can. But I will redo work. I will redo this initialization. I can add this or uncomment this line. So I ask, okay, but I only look at the columns when new col is null to make it a little faster, but I will still go through all these chunks again. So it might be better to do this. What I'm doing here is now I'm saying, okay, give me the smallest ID when new col is still null and start there. So I can find out where did I stop, where did I stop, and where can I restart? Now here is update price simple. This is a relative update. You might remember here that I'm multiplying the unit price by 1.2. Now, if this one crashes halfway through, what do we do now? Well, unless there's something very, very magic about these price values, there's only one choice, and that is to restore and backup. Which, of course, is not a very fun solution if it's a multi-terabyte database. So we need absolutely something which is better. And here is update price resumable. So the first thing I do in this table, I'm checking if this table exists, guest.last ID. The guest schema exists in every database, so I'm using this to put this table a little bit aside because it's kind of a temp table, but not really, because this table has to survive server restarts, so it can handle a server crash. Anyway, I create this table. It's a one column, one row table, and I add the smallest order ID -1 to this table. And when I come in here, I read the smaller chunk boundary is last ID plus 1. It's the same top loop as before, with the difference. I'm saving the upper boundary to this table, so I can find out where I was if I have to restart. And the last thing I do is I drop this table. But again, and the reason I put it in the guest schema because I'm thinking this is kind of a temp table, so I want to put it aside. But I might be overly fancy that. You don't have to put it in guest, but you must not put it in temp to be, because as I said, it must survive server restarts. Now, having seen this pattern, let's go back and revisit some of the other procedures. So this update absolute. So let's say this table is very, very big, and we can only run it as 1 single hour per night. We can run it. And so it's going to take days, maybe weeks before it completes. And so this scan could take a long time. So if we use that technique, we could maybe save this scan and maybe do one or two more chunks of that night to save that time. So it could be more efficient. Or if we take this one up here, the purge operation, yeah, we could do this, but again, this takes maybe a little bit of time. So if you have to restart and do this night after night, maybe we should save these chunk boundaries into a table. And only when we have exhausted that table, we might run this one again, because purge date is maybe going to be one day added. Today, purge date might be let's say the 1st of July. Tomorrow, the purge date will be the 2nd of July, and so on. So you get the drift. But again, we could use this table to save our state so we can quickly restart when we come back. So just to summarize what we have talked about. So one strategy to resume chunking is just ignore and start over. And we can work, that works very well with purge operations and also absolute updates, but in that case, we will redo work. That could be logic in operation to find out where we were. For example, just find the last row we inserted. And we can also add a help table to track where we are, but not in temp delete, must be in the database itself. Or, yeah, restore or backup. And this is where you end up if you don't plan ahead and you don't know much about the operation, because it could be a lot more complex than these canonical things. Let's say you're calling a stop procedure, which you don't really know what it does. So you don't know if it's safe or not. And all of a sudden the operation crashed, or the server crashed halfway through, and just, where do I do now? So you don't want to be that. That's why it's very important. You may not have to code for it explicitly, but at least, because if it's intended to run all at once, but you at least need to have a plan. What happens if it stops and I need to restart? Now, there is actually one more way to deal, one more strategy, and that is just to put it all in the transaction. Because then if something crashes, it will roll back and we can start over. But wait a minute, that sounds crazy. Why would you do that? I mean, the whole idea of doing chunking is to avoid the transaction log exploding, all that. I mean, that was completely contrary to the purpose. But there might be a version to do chunking I haven't mentioned yet. You could run into the situation where you have a query plan where the performance does not grow linearly. So let's say 1,000 rows, that takes 50 milliseconds, 10,000 rows takes 2 seconds, 100,000 rows, that takes, let's say, 40 seconds, and so on. Or it could be a plan that grows linearly to some point, but then starts to spill to disk. Now, of course, in this case, the best might be to address that query, but that may not be feasible. And this actually happened to me a couple of years back. So I had written a procedure that got into levy, I think, was custody fees. And when the customer tested it, it was 140 customers or something. And what I did, I just took all the rows, put them in a table, and which then sent into the procedure. That were a very central procedure in our system that's going to process these. In that procedure, there was a join between two table variables, and that plan was not good for 140,000 rows, I can tell you. Now, the thing is, that procedure is just in so many places, they're just adding up to recompile that. What if we have a loop where we actually send in row one by one? I didn't have the guts. So what I did was, in the outer procedure, I sent in like 10,000 rows at the time, and that worked well for me. Because in this also, notable in this case, if I had removed that transaction, because all of these transactions were supposed to have the same voucher number, so that application impact would have been enormous. I did not want to go there. Now, we should also not forget the risk for bugs. I mean, chunking is not extremely difficult, but if you're sort of coding half asleep at your keyboard, I do that sometimes myself. Yes, sorry. So, coding casually, you might, skip a row between chunks, or process the same row in two chunks and so on, or miss the last few rows, and similar kinds of mistakes. So I recommend that you test on a small data set with small different chunk sizes. Yes, I told you about a generic way to drive chunks, a pattern you can follow. But I know you're going to deviate from that pattern every once in a while, because it will make sense for the particular operation you are doing. So test now with the last chunk full -1, last chunk exactly full, just a single row, and of course verify that all rows are processed. Review your code, have someone else to review your code, and of course a possible add assertions to check. So for example, if you are supposed to copy all rows, check the row count. Also, you can't only test for correctness, you also need to test for performance. But here's a challenge. Because testing all possible small variations is just simply not viable, because it takes too much time. I know, because I ran tons of tests and it took quite some time. Not the least because I wanted to restore the database every time for the next test, so I had the same starting point. And if you have, let's say, your 50 terabyte database you're going to do this work on, that restore is going to take a long time. So you will more or less have to make a choice from gut feeling, but you need to test that gut feeling that the performance is good enough. And keep in mind, you are not looking for the very best top performance. You want to stay clear of disasters. You want to make sure that, yes, it's going to fit into the maintenance window I have for this operation. And also, it's not only execution time, you should also monitor log space and temp-db consumption when you test. Now, I'd also like to put in some general caveats about performance testing. So, if possible, test on copy of production. Well, I would very, very much like to test a copy of production, but in some environments, it may just be a completely no-go to say, well, no, I want a copy of this production database and test. No, you can't do that, because that's this PII data. It's very, very sensitive. But that will be a very big challenge if you can't do that. Now, also make sure that you have the same settings when you test as you have in production. If you have full recovery, and most likely you will have, also have full recovery in test. If you have any sort of snapshot enabled in production, have that in test as well. And keep in mind that if you have an AG with a readable secondary, that will enable snapshot. Accelerated data recovery, another feature that is very important, that it is the same. Now, the hardware should be, well, the same quality or inferior, but not faster. Although when it comes to the RAM, that should be preferably be exactly the same amount of RAM in production as you have in test as you have in production. Because if you have less amount of RAM, the optimizer may make a different choice than it will do in production. And with some bad luck, it could be a really bad plan in production. I actually saw a discussion a couple of years back where they had good performance when they had 352, set max server memory to 352 gigabytes of RAM. And then when they changed it to 356, execution plan completely crumbled because there was a plan change, but that wasn't good. And of course, all depending is how critical it is that you run into surprises in production, because of course this can be quite expensive to having the hardware have taken the time, etc. But if it is a critical operation and it is, we have a very tight maintenance window, by all means make sure that you know that this is going to work out. Also, a little bit about indexes. So first of all, particularly if you want to do this, we have a situation where you have a maintenance window, so you have the database for yourself. Disable non-clustered index and also foreign keys that you don't need for the chunking operation, and rebuild before you're starting and then re-enable them after when you're done. That can help performance a lot because the index maintenance can be quite expensive. And if you're doing something which is going to run in a live environment, it's not very likely that you can do this. You might ask, might it be useful to add indexes to support the chunking operation? Absolutely, because it might make sense to do the chunking operation along the column X because it's very much of the logic. And because you're going to create it once and you're going to see it many times. Could it even be the case that it makes sense to change the clustered index? Well, so it can speed up the chunking part a lot, but then again, you're going to recreate the index twice. And in this case, it even more makes sense to have the non-clustered index disabled. So it can be very, very expensive in full recovery and fill up the transaction log. However, there is something quite interesting that was introduced in SQ 2019, that is resumable index creation. Which, as I understand it, is chunky behind the scenes. I have not actually tested this very carefully, or hardly at all, but it could be quite interesting to study if you have a challenging situation where you would like to do this. Now, so for the last scenario, and that is sometimes all or nothing is not what we want. We're using chunks to handle errors. So let's say we're getting a file with, let's say, 70,000 orders from a source which is not fully reliable. So that could be a product we no longer have, a customer we have blacklisted, or just simply a mandatory value missing. So if we would try to process all these 70,000 rows in one go, one might fail, and we would drop all of the 70,000 on the floor, which would be really, really bad. So we have to run the loop and process them one at a time. No, divide the orders into chunks. And if one chunk errors out, well, you trap that error, redivide that chunk into smaller, and you retry. And eventually, few orders will have to be processed one by one to see out that bad order. So let's have a look at this, and we're going to first look at the script where we are actually doing a clean table loop. So I'm going to start time and after milliseconds, which just takes the 200 solution. I have a row count and the count already and a cursor. And I've set up a cursor over all the cursors in this table called new orders, which is the file I've read, this is my file that I've read into a table. I open the cursor, keep on looping as long as I get an order ID, and then I got a try block, start a transaction, I insert into big orders, I insert the big details, that's all the table called new details, and then I commit transaction. And then I have a catch block, so I roll back the transaction, I capture the error message, and in a real world table, I would log to a table. This is a demo, so I'm doing a raise error. And I do raise error in no way, so I can see this directly. And notice here this is level 16. I also have some diagnostics here. So if I processed 1,000 rows, I'm going to print a message. I'm still using raise error because I want to use this no wait, but now the severity is 0. So this is akin to a print, but it's not buffered. So you can see how far it goes. And then it's also a raise error at the end here. And the last thing I do is I simply delete the new order so that I can do this thing once more. So let's run this and see. Oops, sorry about that. Run this, and we can see here, well, it's progressing with some speed, but yeah. And here you can see there was one error, and that with that order, and one more error. I think there's 4 in total. Yep, there's one more, and I think there's one more before the end. Yeah, and it took almost 30 seconds. So let's now look at the other solution. So again, I got a start time, and after MS, I got a chunk number, I got a row count, and these two are also only help to monitor the solution. I got a table here called chunk sizes, where I simply got the chunk sizes I'm going to try, and those are the chunk sizes I'm going to try: 2,110. And that is actually too many, which I will return to. But I like to have some chunk sizes so that I can, for the sake of the demo. And you might notice that 1 is not here because 1 is mandatory, so it's kind of useless to put that in the table. And I got a temp table here, which is a big temp table. That is, I fill it up with all order IDs and new orders and compute chunks numbers by doing integer division of the max chunk size in the chunk sizes table. Now, I'm not going to do a cursor this time because the chunks are dynamic, so I'm just going to keep on looping as long as I have data in the temp orders table. And you may notice here that the while block is there's a begin try for the entire while block. So there's a try catch for all the entire while block, or the entire while loop. So I get the smallest chunk number I have in temp orders, start a transaction, try to insert all these rows in new orders for this chunk, and also new details. Again, doing you exist here against temp orders. Do a commit, some diagnostics. So if I have processed more than 1,000 rows, I'm going to print out the diagnostic message. Again, that's 0, not 16. And I'm going to delete that chunk at the end from the temp table. Now my catch block. Okay, if I have open transaction, row back. 2 more variables. So I get what is the current chunk size of this chunk. And if that chunk size is bigger than 1, then I should get the new chunk size, which is the next value in the chunk sizes table. And if there is no anyone, well, the new chunk size will be 1. And again, there's a diagnostic message. Again, it's level 0 down here with no weight. And then I'm going to compute the new chunk numbers. So I got a CTE here, which I return the chunk number as something I call temp chunk. Temp chunk, I'm doing a row number again and doing an integer division with a new chunk size. And then I'm going to update that back to the temp table. And you might think I need to join the CTE with the temp table. No, I don't need to do that. I can update the CTE directly. Yes, I know this looks scary. Does this really work? I thought the first time I saw it. Yes, it does. So what I do is simply I take the temp chunk and I add the max chunk number in temp orders, so I get the new chunk numbers. But if I had a chunk size of 1, this means that, okay, this was a bad order that I should signal, so I get the error message, I get the order ID, and then in this case, erase the message. In the real world application, I would have logged it. And also, again, delete that chunk from the temp orders table. So let's run this and see how it runs. And you can see it goes on quite a lot faster. And you can see there was a redivision, so that was an error. And all errors will now come at the end. And the total was less than 7 seconds. So it was an improvement with more than a factor of 3. So that was actually quite a bit of gain by doing chunking in this case. Now, a few more things here to consider. So picking the initial chunk size is a little difficult. But first of all, because if you set it too high, well, then there will be errors in about every chunk. So that's not efficient. You want most initial chunks to be without errors. So here is my rule of thumb. Absolutely not based on any science or investigations, just taken out of thin air, more or less. If you expect 1 row, or by common sense, you could also say, 1 row of n to error out, well, set the initial chunk size to n divided by 10. Assuming, of course, there were other limitations like having been nice to others, avoid log escalation, etc. Now, of course, what is the value of n? Well, that may require some good gut feeling. Of course, if you already have a process where you are running one at a time and you want to rewrite it to do chunking, then you might have some data you can work for. Else you would just have to, what is reasonable, and make some guess. Also, one thing to consider here, though, is are the arrows coming in bursts or are they completely random? Because if they come in burst, your chunk size can be a bit bigger, and then they are completely scattered and completely random. Because if they come in burst, one chunk will have lots of errors, most other chunks will not. And when you divide by chunks, as I said, the demo I had too many chunk sizes, divide by at least 100, maybe 1,000 at a time. I know we did this at a place I was, so there was a procedure that or process that took one at a time, and he was slow, and it was also very complex, had been changed a lot of the times. So he was really in need of a cleaning up. I wrote the spec, and a colleague of mine, he did the implementation, and he went for 1,000 at a time, and if that failed, he would take one by one, which I think worked out quite well. So we're coming towards the end of this session, and here is a summary of what I've been talking about. So chunking is nothing you use every day. I mean, it's a trick we have in the toolbox for these really large operations when we encounter them, to keep the transaction log and the temp to be in check, and to avoid conflicts with the rest of the system. So make sure, I like to remind you again, make sure that you have transaction log backups running and with a high frequency. And indexing is critical. Your chunking must always follow an index, preferably the clustered index, because repeating scans is going to be extremely expensive, and it's not going to be fun. The top method is a very generic way to drive the chunks, and it works with about any data type you can put an index on. And it works even with non-unique indexes to some extent, as long as you can deal with that. The chunk size is very little bit in size. For multi-column keys, only work with that second level if you really have to. And defining chunks and temp tables is less efficient than extending the top method, but it's just so much simpler. And make interval variables known to the optimizer with either option recompile or sniffable with dynamic scale. And dynamic scale may benefit from full scan statistics. Don't forget to consider how your applications may be affected. What happens if the chunking is interrupted? Design your loops to be able to restart when they were interrupted, or at least have a plan for it. And if needed, create a help table to track where you were. And don't forget to test for correctness and for performance. So this is the last chunk. My name is Erland Sommarskog. My email address is sql@sommarskog.se, and you're more than welcome to drop me a line if you have anything related to this session. Actually, one more thing I'd like to add. I mean, I have basically only skimmed at the surface of this complex topic. I mean, this is nothing we do every day. So every time we do this, we might do some new revelations, some new experience. So if you run into something you want to share with me, I would really much love to hear from you. Slides and scripts for this session is available at my website, sommarskog.se/present. And you can also find BigDB here. And it's the download is 3 gigabytes, and the full database is 20 gigabytes. And you need at least SQL 2016. So let's see. Someone had to, I see some people have to drop out.
Yeah.
But as I said, this ran a little longer than 1 hour.
No worries, no worries. This was a really great session, and I've actually already had a lot of requests on the side to asking about the recording because they couldn't join today. And as you mentioned, some people dropped off, so I'll be sure to get this recording up quickly. I know this is really relevant for us at our company because some of our ETL processes have really large tables, and now I'm going to be kind of re-looking at this recording again myself to see how we may be able to implement this with some of our ETL things that may need it. We use batching in those instances, so I'll relook at it. So really, really great stuff. I'm excited about.
Oh, great.
Thank you so much. I know it's getting late where you are, and we really appreciate you speaking for our group. Thank you, everyone, for joining us, and have a great day or evening or whenever you're seeing this. And thanks for joining us. Bye-bye.
Yep. Bye.
Yeah.